On the volume itself, let's change a few things. So the swirl size should be smaller because remember, our object isn't all that big. Let's make sure we have our robot visible. The other thing we can do is instead of making it smaller, we can play with the granularity of the volume. So it'll have a bit more irregularity to them. Then let's add another layer of turbulence, and this should be okay. Maybe the swirl size can actually be a bit bigger so we can actually identify what's happening a bit easier. 0.6. Yeah, let's give this a try. So this is our test. Let's create a null and let's call this out null out val vol a. Now let's apply this to our particles and see how this is looking. So let's go to the development blast. I'm going to reduce the scanner again, so not interested in going full throttle yet. And let's have inside. And we want to apply everything. So the order isn't very relevant, but it is somewhat relevant. Pop fluid should be the last one. Just keep that in mind. And let's put an pop advect by volumes. Let's choose our volume. Field is val, that's correct. Advection type, update force or update velocity. If you use update force, what's going to happen is it's not going to go into the shapes that we're looking for as easily. If you do instead update velocity, that's going to be much faster. Let's have a look at how this works. Let's turn off pop fluid. Let's turn off the static object we have here. We can even turn off pop attract just so we can have a look at how this is going to work. Okay, pretty cool, right? Pretty crazy stuff going on. The issue here, it's going to be reaching the limits of our volume bounds, and it's going to pretty much stop. But really cool effect. This is not all exactly what we want, so we do intend it to kind of be projected, and then to make sure that this is applied to it, we could go with two different approaches. I'm going to show you two different approaches to do this. So we could go with an approach where you create a pop group, and let's say these are the ones that I want to be called. So let's call it to advect. And then we enable this rule and we'll say that we want to be in group all the particles whose age or whose age, so normalized age, is bigger than 0.5. All particles that are older than half their lifespan will be affected by this pop advect by volumes. Okay, and so let's grab this group and make sure that the pop advect by volumes will only affect that group. Control V. This is definitely one way to go. So they go out, and then after a certain point, they start getting affected by this. Let's turn on our static object. And by the end of their lives, we do get some more interesting shapes, as you can see here. Okay. And this is what we were missing for sure. This type of interesting shapes that we get here and there. So this is a good idea, but we're not there yet. So the best way to apply this isn't exactly based on such a rigid transition where you have particles that are not being infected and then suddenly they're being infected. That's definitely not the best way to do it, but it's one way to do it and may be useful for other applications. But in our case, we're going to be using a different approach. So let's create a copy of this. Let's make sure it's not applied to just any group in particular. And then let's connect this here instead. And in fact, what we're going to be using is the velocity blend. We're going to use vex expression. And this is going to be much better. Okay, so what we're going to be doing is instead of having a rigid transition, we'll write a piece of code that will allow us to actually have a soft transition between the particles that are not being advected and the particles that will be advected. And that's a pretty straightforward expression. So we just look for the name of this parameter, hovering over it, so val blend. And let's say that val blend is going to be multiplied times equals a ramp called advect or val blend or blend ramp. Val blend, let's go with that. Val blend. And it's going to be analyzing an age, normalized age. Now let's create this magic button to create the parameter in our interface. And now all we want to do is kind of draw a nice little curve here. Let's switch the interpolation to B-spline. This down, add another one here. So we really want them to be affected more as they get closer to the end of their lives. So not in the beginning at all, but they start to be slightly affected and then very much so. And you'll see that the transition is going to be much more organic. Okay. They slowly start to be driven by that velocity blend with of the effect by volume. Of course, you can draw the curve however you prefer, but this seems like a nice starting point. The issue right now is definitely that our velocity volume isn't all that interesting. It already has something going on there, which is great, but it can be better and we will make it better. But this is a starting point. Cool. One thing I want to make sure I don't forget to apply is here on the pulp fluid, the particle separation. I'm thinking of taking this value down. Instead of multiplying it by 2, I want to check it out with this because I think particles could be getting closer to each other, and we could have higher density areas of particles if we don't have that. When we're using pulp fluid, of course, when we're not using pulp fluid, it doesn't really matter, of course. But I think this will be an interesting addition. Let's see. I may have forgotten to adjust this, the neighbor size. Yeah, it's pretty big. Yeah, this is much faster. Let's see how this looks.